geometries, this valence shell electron pair repulsion theory, again, just to sort of bring you back up to where we were on Friday of last week. All these electron pairs that are around the nucleus, the valence electrons are the ones that do the bonding. And so those valence pairs, we can calculate sort of where in space they're going to be so that they get the farthest separation from one another. Of course, we know electrons don't like to be around other electrons. Negatives and negatives repel. And so that's how we come up with these geometries. And experimentally, things fit pretty well. And so we think this is a pretty good theory. We left off talking about what happens when we have 5 bonds around our central atom. And so we talked about how there's sort of 2 sets of bond angles. There's one that we call the equatorial bond angles, and that's just essentially a trigonal planar geometry arrangement where we have our central atom and 3 atoms that are bonded to it in a plane. They take on that triagonal shape, and they have a bond angle of 120. And then we call them the axial atoms, those ones that bond above and below that plane. And those have a 90-degree bond angle to the equator. Okay. We call that trigonal bipyramidal. Again, that's both for the arrangement of electron pairs and for the molecular geometry. And if we were to do an example, PCl5 is what we would do. And so we've got our phosphorus with our chlorine atoms. Again, because now we're in 3 dimensions, we have to figure out a way to represent those. And so we have one coming forward and one going backwards. We need all of our lone pairs around our chlorine. Don't forget that for a full Lewis structure. We've got to have all those valence electrons represented. And there we go. Remember we talked about how for tetrahedral, we would see lots and lots and lots of examples that are tetrahedral in shape because that's 8 electrons. That's a nice full octet. Here you see we have 10 electrons around that phosphorus, 5 bonds with 2 electrons each. And so those phosphorus can have an expanded octet. It's in the n=3 shell. And so it has those empty d orbitals for it to store those extra electrons. I'm just going to mark here that we call these 3, right, the equatorial set of atoms, and we refer to these 2 as the axial. Okay. All right. So the last one that we see would be if we had 6 electron groups, and so for us that's 6 bonds around that central atom with no lone pairs, and we call that an orthogonal geometry. Okay. Orthogonal just because in mathematics, if something's orthogonal, right, we say that they're 90 degrees from one another. In an orthogonal molecule, all of our bond angles are 90 degrees, and so that's where that comes from. I don't have room to draw it out here, but let's move on to the next slide. And we'll talk about sulfur hexafluoride. So SF6. If we think about this as having 6 fluorine atoms coming off of it, it could be that 4 of those fluorines are in the plane of our screen. One of those fluorines is coming straight out in front of the sulfur, and another fluorine going straight back directly behind the sulfur. Now, we've done the wedges and dashes for things that are in front and behind one another, but we don't really have a good way, and chemists don't use any method to represent 3 atoms in a line, right? The wedge and the dash shows us what's in front and what's behind, but we haven't developed a method to show us what's in front, what's in the middle, and what's behind. And so instead of writing 4 fluorines in the plane, one in front, one in back of the sulfur, we only draw 2 fluorines in plane, and then 2 coming forward and 2 going backward. Okay. And so we've got 2 of our fluorines that come out of the plane at us. And 2 fluorines that go back and again, I'll try to draw those fluorines that come forward just a little bit bigger. The fluorines that are small are in the back, just to provide maybe a little bit of perspective, help us visualize that maybe a little bit easier. And so hopefully you can see that, you know, we've still got these, all these positions are equivalent. And so we can rotate this molecule in space, and any pair of fluorine atoms will make a nice axis. And so we don't really differentiate between axial and equatorial in this geometry. All of our bond angles are 90 degrees. And so, again, that's why we call this octahedral. Is that what I call it? I said orthogonal. Orthogonal is, in fact, what's meant by 90 degrees. I'm terribly sorry. Octahedral is the name. My apologies. Octahedral. Okay. Octahedral is the name. Orthogonal is sort of that setup where they're all 90 degrees from one another. So octahedral. If you'll allow me just a small minute of going off on a bit of a tangent here. When we have a tetrahedral, we have these, let me draw this one a dash. When we have a tetrahedral molecule, we have that central atom, and then those 4 bonded atoms to it form the 4 points of one of these triangular pyramids. The 4 points of that triangular pyramid form 4 different faces. Right? And so we've got this face here, we've got this face here, we've got the face on the bottom, and then the face on the back. And so 4 faces. That's where the tetrahedron name comes from. Tetra for hedron, heads or faces, and so that's where the name comes from. For an octahedral, you've got, I'm gonna be really bad at drawing this. But you've got your 4 faces now because it's octahedron, but you got 4 faces on top of your pyramid, 4 faces on the bottom, and so you have 8 faces, and so that's where the term octahedron comes from. Okay, so there's our octahedral. So these first 5 geometries are the geometries that arise when we have no lone pairs, and we'll talk a little bit more about multiple bonds and how they behave, but without any lone pairs. Now, we've drawn a lot of Lewis structures. We did a whole lot last Thursday in lab, and you saw that we had lots of structures where our central atom had a lone pair. And so we're going to go through and talk about what some of those geometries might look like. So if we've got 3 electron groups, we're going to add to this an A, B2, and E. So AB3 means that there are 3 bonded atoms and no electron lone pairs. Right? And so now that we have 1 electron lone pair, we've got 2 bonded atoms and electron lone pair. And so we have a 2 and a 1 here. Because this arrangement of electron pairs, there's still 3 electron pairs. It's just that instead of all 3 of them being bonds, now only 2 of them are bonds and 1 of them is a lone pair. This arrangement doesn't change. So this is still trigonal planar. Not a B. But now, if we think about a molecule like SO2, SO2 is a good example. He has 18 valence electrons. We put an S in the middle. We put our oxygens around. That's 16. That's 18. Our sulfur doesn't have a full octet. And so we're going to push these pair in to form a double bond. If we do a quick formal charge analysis, we have a 0, a +1, and a -1. What can we do with a +1 and a -1 next to each other? To make them 0?
Double bond.
Make a double bond. Sulfur already has 8 electrons. Can he handle 2 more from a double bond?
No.
Yes, he can.
Oh.
He's in the n = 3 level. He can have an expanded octet, right? And so he's cool with having more than 8 electrons. And so he's going to make 2 double bonds here so that he has an expanded octet, but that all the formal charges are 0. And so if we look, this falls into our qualifications here. We have how many atoms bonded to the central atom? Well, 2. How many lone pairs on the central atom? Well, 1. And so if we try to put those in space as far apart from one another as they'll go, it'll end up looking something like that. Right? Now, some places you'll see this lone pair that's sort of drawn in a balloon. Whoops. It kind of looks like this. Right? That's to show that those electrons actually do, take up some space. They're in an orbital. They're in some area around that central atom. And so they do occupy some space. And so in this SO2 molecule, if we look at the electronic geometry, or this arrangement of the electron pairs, it still forms that triangle. Right? And so we still have a trigonal planar electron pair geometry. But if we look at just the atoms in our molecular geometry, we just sort of have this, this boomerang kind of shape almost, right? And we call that just simply a bent geometry, right? It's not linear like we had with our beryllium dichloride, BeCl2, but it's a bent shape. Okay. Now for trigonal planar, what was the bond angle?
120 degrees.
Yeah, we had 120 degrees. Now, this lone pair up here, he is not sort of stretched out between 2 atoms. That pair of electrons is sitting all on that sulfur. He's in an orbital, but it's on that sulfur. He's not shared between 2 atoms. And so it turns out that electron pair that's not bonding to anything takes up a little bit more volume close to that sulfur atom than the bonds do. Again, since this is electron shell repulsion theory, if he's a little bit larger than those bonds are, he's going to push those bonds away from him so that he repels them a little bit more. And so there's a little bit extra force, right? So lone pair repels more strongly. So that lone pair repels more strongly. And so if I were to ask you to think about the bond angle here between our atoms, what would you say? If we know it's 120,
It's smaller than 120.
say again?
It's smaller than 120.
Yeah, exactly. I'm not looking for a number here. I'm just looking for, generically speaking, this is going to be less than 120 degrees. Okay. Because it's going to be different for different molecules. Because these are double bonds instead of single bonds, it's not going to be that much lower than 120 degrees because these are each 4 electron groups, right? And so they occupy a little bit more space than just a single bond. And so it's not really going to be that much less than 120 for this particular example. All right, now when we have 4 electron groups, like I said, this was tetrahedral, and this is the biggest. We'll find lots of examples here, but if we just add in 1 lone pair, so we've got 3 atoms and 1 lone pair, it's still tetrahedral. This column is not going to change. It's going to be tetrahedral. But now we've got our molecular geometry, and a good example here is ammonia, NH3. And so I'm going to start drawing it in the way that we would draw a tetrahedron, right? And so I'm going to draw it with my lone pair up here, my hydrogen here, here, and here. Okay. Now, you don't have to make the lone pair be in the plane. You can switch it up a little bit. I do this just because it's easier for me to think about in 3 dimensions. But now, instead of having this full tetrahedron, we now have, we form kind of a triangle of our base here. Our hydrogens all form a triangle. But because there's that little lone pair at the top, right, this is no longer a flat one plane molecule. These hydrogens are a little bit below that nitrogen. And so we call this geometry trigonal pyramidal. Trigonal pyramidal. What did we say that the bond angle was for tetrahedral?
109.5.
That's it. I'm A-okay if you remember 110 degrees. So either 110 or 109.5, either one of those is A-okay. But our trigonal pyramidal is going to be just a little less than, oops, not 100. Going to be just a little less than that 110 degrees. Okay. All right, so if we move on, we could replace 2 of these with lone pairs. Still a tetrahedral electron geometry. Water is our best example. We all know water. He's got 2 bonds and 2 lone pairs. Well, we've seen this geometry before. And so we just call this a bent geometry. This hopefully shows you that we need to know a little bit more information than just the molecular geometry in order to really know something about the shape of the molecule. Because we have what we call a bent geometry in both the tetrahedral electron geometry and in the trigonal planar electron geometry, those are going to have different bond angles. One of those is going to have one lone pair, one of those is going to have two lone pairs. And so we need to know more than just the molecular geometry if we're going to know something about that molecule. Okay. To show you the difference in bond angles, in water in particular, I just happen to know that this is about 104.5 degrees bond angle in water. And so it decreases by about 5 degrees going from pure tetrahedral to bent. All right. Now, if we removed it even further, we just have two atoms, and two atoms is always going to be linear. So this is just a little bit more of that information talking about how when we have lone pairs, we distort those bond angles just a little bit. And so in ammonia, MH3, they are a little bit closer together, about 2 degrees, we're in 107. And then in water, we get down 5 degrees, 104.5. These images out of our textbook are also a little bit better at showing that trigonal geometry, that trigonal pyramidal geometry in the NH3. Again, you have your trigonal base here, right? But you're forming a bit of this pyramid with those nitrogen-hydrogen bonds. Now, some of you may say, but wait, isn't that still four-faced? Yes, it is absolutely still four-faced, but not all four of those faces are equal in area, equal in size. And so we don't call it a tetrahedral molecule, a tetrahedral shape, because those four faces are different. So trigonal pyramidal, because it's not trigonal planar. And again, here in the water, we just have our bent geometry. Any questions so far about adding in these lone pairs to our molecular geometries? All right. Oops. So when we jump up to 5 electron groups and we add in one lone pair, we've got 4 bonded electrons with a lone pair on that central atom. It's still going to be trigonal bipyramidal, right? Remember, this column doesn't change for us ever. Okay. But now we have to think about, I'm just going to draw a generic molecule here. We've got two sort of different classes of molecules. We've got those equatorial positions and we've got those axial positions. And we have to figure out where our lone pair is going to go, right? Which of these locations is more stable for a lone pair? Now, does a lone pair want to be really close to other bonds or really far away from other bonds?
Far away.
Far away.
Yeah, far away. And so if we look at this, shape here in red, you can see that if I chose an axial position, that lone pair would have 90-degree bond angles to 3 different atoms, right? So 90-degree close to 3 different atoms. However, if I took one of these equatorial positions, he'd only be 90 degrees to 2 different atoms. Right? And so it turns out that being farther away from more atoms is more beneficial for that lone pair. And so it turns out that this equatorial position becomes a lone pair. Right? I'll get rid of that bond since there's no bond there, but we can think about this as occupying an orbital. And so the fun name that we have for this one is a seesaw. Okay. Let me sort of redraw it here. You can imagine that these bees form, the bees on the bottom form the legs, and the bees that are in the axial position form the seat. And so this seesaw just goes back and forth on those little bee legs. And so we call this a seesaw. A more proper definition is a distorted tetrahedron. Because you still have your four faces. They're just, you've got one, yeah, it's hard to draw, but you got this one on top, you got the one in the back, you got the one underneath there, and then you got this one in the front. And so you've got your four faces, but it's just a little distorted. Seesaw is a-okay with me. I think, as a matter of fact, the ACS final uses the term seesaw when they ask about this particular geometry. So, right. Moving right along, we have, if we have three groups with 2 electron lone pairs, again, this trigonal bipyramidal continues. Now I'm going to redraw our molecule. With our lone pair already in an equatorial position. Now, if lone pairs don't want to be next to bonds, lone pairs for sure don't want to be next to other lone pairs, right? And so if we took it from an axial position, right, that's still 90 degrees. But if we take it from an equatorial position, that's 120 degrees. And so this equatorial position is, in fact, the best place to take it from. And so you end up with another lone pair in another equatorial position. Okay. And so now that we have 2 equatorial positions gone, we can rewrite our Lewis structure this way, with our axial atoms forming a line. We've got one lone pair over here, we've got another lone pair over here, sort of bunny ears, and then we've got this B down at the bottom, right? And so now all 4 of these atoms are in a plane, and the 2 lone pairs are coming in and out of the plane. There's a pair coming forward, and there's a pair going backward. We do not have to draw wedges and dashes for lone pairs unless you're just really like getting creative. And so this one is very uninteresting in terms of a name. We call this T-shaped. Okay. All right. Now you can use your chemical intuition. If we were to add one more lone pair, would it be one of these 2 axial positions, or would it be that last equatorial position?
Equatorial.
Equatorial.
Yeah, it'd be that last equatorial position because it's still 120 degrees away rather than 90 degrees. And so for this last one that we'll talk about, we've got AB2E3 with 2 bonded atoms and 3 lone pairs, still trigonal bipyramidal. But now I've got my A in the middle. I've got a B and a B in my axial positions. I've got a lone pair over here. I've got a lone pair over here. I've got a lone pair over there. And now what's my bond angle? What would we call
180
this?
degrees.
180.
Yeah, 180 for sure. And so we're back to being a linear geometry, molecular geometry, with a 180 degree bond angle. Okay. Moving on to 6 electron groups, our last set of electron groups. If we replace one of those bonded atoms with a lone pair, we've got 5 bonded atoms, 1 lone pair. We're still going to call it octahedral. Because these are all at 90 degrees from one another, it does not matter which one of those first ones we pull off and replace with a lone pair. Just for the sake of drawing things, I'm going to make my lone pair be at the bottom. So my bonded atoms are going to still come in and out of the board, as well as this one position at the top, okay, with my lone pair down here. Okay. Now the base of this molecule, these 4 central, these 4 atoms that form the equator, form a square. Okay. And then because we just have that one atom above it, we end up with this square pyramid, this sort of standard pyramid shape. Let me make that one dash so we know it's behind, right? And so we call this square pyramidal. So again, that difference between these last 2 columns, the arrangement of the electron pairs takes into account the lone pairs as well as all the bonded atoms. The molecular geometry only takes into account the atoms, right? So I don't care about where those electron pairs are when I do my molecular geometry. All right, for the next one, AB4E2, still octahedral. Now, I've taken off one lone pair already. In the previous example, I took it off at the bottom. Now, when I take off another lone pair, do you think it's going to want to be one of these 4 that form the base of our pyramid, or is it going to be the top of our pyramid?
The top.
The top, yeah. It's going to get as far away from that other lone pair as possible. And so we end up with our A in the middle. And then I'm just going to draw it this way. Because they're all fitting in one plane. We've got a lone pair in front and a lone pair behind. Again, we don't have to worry about wedges and dashes for our lone pairs. Okay. And now that this is all in one plane, our atoms are all in one plane, they still form a square, but now it's not a pyramid, so we just call this square planar. Okay. Square planar. Okay. Now, the last 2 for for octahedral, you know, if we took off 1 more, we'd be to T-shaped. If we took off 2 more, we'd be to linear. And so those are very similar to the trigonal bipyramidal, and they're much less common. You see those shapes much less commonly than you do these trigonal pyramidal, square pyramidal, and square planar geometries. Okay. And so this is a table out of our textbook, table 10.2, that sort of shows all of these, let's call them secondary molecular geometries, right? Where you have the introduction of a lone pair. All right. Okay, so now that we have covered all of the possible arrangements in space of all of these atoms, we're going to take a minute and revisit a topic that we discussed in chapter 9. Well, let's do some examples, and then I'm getting ahead of myself. All right. So we need to draw some Lewis structures so we can figure out the number of bonds and lone pairs, right, for all of these. Let's take a minute. I'm going to do A and D. We're going to do a lot more of these in lab on Thursday, and so I don't want to spend a whole lot of time here in class. But let's do A and D real quick. If we look at arsenic, AS, arsenic is just below phosphorus and nitrogen. So he's got 5 electrons. And so he's going to bond with hydrogen this way. So we have 8 electrons total. There's 6 already with a lone pair. 3 bonds and a lone pair. What's our molecular geometry?
Trigonal pyramidal.
That's it. In Thursday's lab, I'm going to ask you to actually take this one step further and draw the molecule in its appropriate geometry. And so if we were to do that, it would look something like this, right? Using that geometry and those wedges and dashes to show what that geometry is, right? I3 minus, iodine has 7 valence electrons, so that's 21 plus 1 for the minus, that's 22 electrons. Well, you bet we're going to have an I in the middle and an I on each side. 2, 4, 6, 8, 10, 16 electrons. I filled up the octet on my peripheral atoms. I still have leftover electrons. I'm going to put those on my central atom. And that should be 22 electrons total. Now, since this is an ion, I need my brackets and my charge. And what would the molecular geometry of this one be?
Is this one bent?
It's not bent.
Is it linear?
Yeah, it's linear. So we've got 5 total electron groups. Let me circle those. 1 here, 1 there, 1 there, and then each bond counts as a group. And so this would be like A, B2, because we have 2 bonds, E3, because we have 3 electron lone pairs. This was a linear molecular geometry with a trigonal bipyramidal electronic geometry. Okay. Yeah. So we'll do a lot more practice on that in lab on Wednesday. Thursday's lab. So now we're going to jump back into chapter 9 where we talk, back to chapter 9 where we talked about the polarity of individual bonds, right? We looked at the electronegativities of the elements and we said that the example that was in the problem set was if this was hydrogen and this was fluorine, because fluorine's more electronegative, it sort of hogs that electron density. The electron spends more time around fluorine, and so it's a little bit more of a negative charge, and so we gave it this partial negative. Remember, delta is a partial when we talk in mathematical terms, leaving this hydrogen with a partial positive charge. And so this is a polar bond. Because this is just a 2-atom molecule, this is a polar molecule as well. But now we're going to start talking about this term dipole moments. When we talk about dipole moments, this is the sum of all the bond dipoles in a molecule. And so if it's a nonpolar molecule, the dipole moment is 0 or very, very small. If it's a polar molecule, then all of those bond dipoles add up to something that's not 0. Again, since this is a very simple molecule, there's only one dipole because there's only one bond. When we draw bond dipoles, we represent them as vectors, and vectors are just arrows. And we always point from the partial positive side to the partial negative side. And so let me write that out in words first. And so it's a vector from the partial positive to the partial negative. Okay. And so for HF here, we're just going to draw it this direction. Okay. I'm not, at this point in your chemical career, I'm not super interested that, you know, if it's more polar, the vector should in fact be longer because the length of a vector indicates magnitude, right? We're not going to get sort of that deeply into the mechanics of dipole moments and vector addition and all that good stuff. I just want the general picture of is it polar, is it nonpolar? Okay. Now, the way that we sort of represent and the way that we remember and the way that we draw dipoles is to mark the partial positive end with a little plus sign. And we just do that by crossing the tail of the vector. That helps us know that we always start our vector at the partial positive end, and we direct that vector toward the partial negative charge. Okay. And again, we only would draw these for polar bonds. We would not draw them for nonpolar bonds because they don't have a bond dipole. So doing a quick example here for NF3 versus NH3. If we look at our table of electronegativities, hydrogen is less electronegative than nitrogen. And so all of the bond dipoles point from hydrogen to nitrogen, right? So they all add up that direction. And then, of course, electrons are more negative than any atom. And so we have another dipole there from the nitrogen to the lone pair. Because sort of all of our dipoles are pointing in the same direction, you see here in green, I'm still drawing in white, that doesn't work. You see here in green that we have this overall dipole. This is the sum, right, of all these vectors, of the red vectors. And it's pointing up. What that means is that down here, sort of the bottom side of that NH3 molecule, right, that's where the partial positive is. And up here at the top where that lone pair is, that's where the partial negative is. Okay. For NF3, things take a bit of a turn because fluorine is more electronegative than nitrogen. And so now all those nitrogen-fluorine bonds are polar, but in the opposite direction, right? They're polar with the dipole, the bond dipole pointing toward the fluorine atom rather than toward the nitrogen atom. And so again, this green arrow is the sum of all of our red dipoles added up together. And because it's pointing from top to bottom, that means that the partial positive charge is actually on the side of the molecule with the lone pair, right? Which is a little weird to think about, but that's the way it works out, that the partial positive is on the side of our dipole that has the positive charge, and the partial negative is at the bottom of our molecule. And so the partial positive at the top and the partial negative at the bottom, exactly opposite what we saw with NH3. Okay. So let's see if we can do a quick example real quick. BRCL, this one is a little bit too easy for us because it's just two elements, right? But between bromine and chlorine, which one of those is more electronegative?
Chlorine.
Chlorine. So he's got a partial negative. Bromine has a partial positive. I'm going to draw my bond dipoles in red. Should I go from chlorine to bromine or bromine to chlorine?
Bromine to chlorine.
That's it. Right. So yes, it does have a dipole moment. Right, done. Let's take a look at BF3. Now, if we didn't know anything about our geometries, we might write BF3 like this. Right? And if we did that, which of these is more electronegative, boron or fluorine?
Chlorine.
Fluorine for sure. Yeah. Right. If we did that, we might draw our bond dipoles this way. And we might say, okay, the one on the left and the one on the right cancel out. And so the bond dipole, the overall dipole must be from the boron to the fluorine at the bottom, right? Don't do this because you know geometry now. You know that with three bonds, we're going to form a trigonal planar geometry. Let me go ahead and draw in all of our individual dipoles. Who can, excuse me, who can tell me a little something about vector addition? Have you talked about that in physics yet? Maybe not.
Add them up, and I had JCat and IJK at component. You add them up as separate components, right?
Yeah, we're adding them up. And the term that I like to use is tail to head. Is that familiar to anyone?
Oh yes, sir.
Yeah. So I'm going to start with this one that goes up. All right, and there's my first dipole, bond dipole. I'm going to add all the others up, but I'm going to essentially start drawing at one point, and I'm not going to stop drawing until I'm done with all my vectors. Right? And so that's 1, 2, 3. So that's 1. Now the tail of the next vector starts at the head of that vector. There's 2. Three. And so, maybe the bond angles that I have drawn are not perfect, but we know that they're really perfect in nature. These are all at 120 degrees. And so I started and I ended at the same spot. And so there is no bond dipole. There's no dipole moment. Because I started and ended at the same spot. All right. If you have any questions about this stuff, show up on Wednesday. We'll work a few more examples, both of determining molecular geometry and of drawing dipole moments, and then I'll answer any questions you have. But we'll apply a lot of this stuff in lab on Thursday. Okay? Sorry I kept you a little long.
Thank you.
Thank
Thank you.
I'm going.
Thank you.
Thank you very much. Have a fantastic day.
Yeah.
Oh, also, Dr. Davis,
Yes, sir.
I do have one thing to tell you, which is on class on November 30th. I might not be able to attend because I have a neurology